Let's take a look on this video at a couple of improper integrals type 1. So we're going to be looking at some integrals that are on infinite intervals. That's quite a mouthful, but let's go ahead and take a look at a couple of these. And remember from our previous video where we introduced this topic that we were talking about how we will replace the bound that is infinite, so whether it's the upper bound or the lower bound of the integral, we will replace it with a value t. I use t, you could use a or b if you prefer. We're going to replace it with a t, and we're going to take a limit as that value t is approaching either infinity or negative infinity. We're going to take the integral, evaluate the limit of that integral as t is approaching infinity or negative infinity, and if we get convergence, if that limit exists, then we're going to say that our integral is convergent. And if we get a limit that does not exist, including if it is infinite, we're going to say that the integral is divergent. And if we're across an interval from negative infinity to infinity, the last bullet here on the page, if we're across an interval from negative infinity to infinity, then we will just break it up into two pieces and look at each piece individually. I have some real rough steps sketched out here on the screen as well. We can always just replace our infinite bound with t, integrate, take the limit, determine if we have convergence or divergence. So we're going to jump right into it and illustrate some of those points on the examples. So here we go. We know that this is improper, first of all, an improper integral, because we have that infinite upper bound, that upper limit of integration. We're integrating from 0 to infinity. And so the very first thing I'm going to do is say I need to replace that. I have to replace that with a variable t, and I'm going to be taking the limit as t is approaching infinity. I'm going to go ahead and jump into this a little bit with the integration strategy at the same time. When I look at this integral, I can see that it's a rational function and it is factorable. So I'm going to jump right into factoring that rational function, x plus 2 x plus 1, thinking ahead to the fact that I do need to integrate this, and then I can evaluate it across those bounds and take the limit. So I'm going to integrate it using partial fraction decomposition because of that factoring into those two linear factors. And we're going to go ahead and do that. I'm going to speed up the video a little bit through this because this hopefully is just quick review. And once we've got the integral, we'll come back and okay, so I have the integral. I simply used a little bit of partial fraction decomposition. I got into those each of those individual integrals of 1 over x plus 1 minus 1 over x plus 2. Did a quick little use substitution. I think at this point we can, a lot of us might be even skipping this little use substitution, but be careful of that. If there were any constants, you'd want to make sure if it was 2x plus 1, you'd want to make sure that you adjusted for that in the substitution. Okay, once we've gotten to this point, we are now going to evaluate across the bounds. Now remember, the bounds are from 0 to t, so we're going to evaluate across those bounds, and then we're going to take the limit. So let's go ahead and do it. So we're going to take the limit as t is approaching infinity. We're going to get the natural log. By the way, I also combined my two logarithms. I think it'll make it easier for this step. So t plus 1 over t plus 2 minus, when I plug in 0, I get the natural log of 1/2. Okay, so we've got our integral, we've got it evaluated across the bounds from 0 to t, and now all we have to do is take the limit. So notice when I take the limit, obviously the limit of the constant will be itself, so I won't have to worry about that. But notice when I take the limit of the natural log of t plus 1 over t plus 2, I get the natural log of infinity over infinity, which I hope is bringing some caution to your mind. When we see that infinity over infinity, that is an indeterminate form. So infinity over infinity is indeterminate form, but we have a way to deal with indeterminate forms. We can bring our limit inside that logarithm and look at that indeterminate form because a natural log function is a continuous function. So our limit can come inside that continuous composition there, that composition of continuous functions. It can come inside of that logarithm, and we can consider what's happening to that function t plus 1 over t plus 2. And since it's indeterminate, we can use L'Hopital's rule. So I indicate L'Hopital's rule. I'll highlight it here. I indicate that I'm using L'Hopital's rule with a little LH on my equal sign, and now I'm taking the limit as t is approaching infinity of the natural log. Well, when I take L'Hopital's rule of the top there, I get 1 over 1, and we already have evaluated, this is outside of the limit, so I'm going to go ahead and pull this out, natural log of minus natural log of 1/2. When we took the limit of the constant in the line above, it was, of course, just the constant. It was that issue with that infinity over infinity, but we have a way to deal with that. This is where we're going to employ our skills with limits. And so now we're taking the limit of 1 over 1, but the limit of 1 over 1 is 1, and the natural log of 1 is 0. So this becomes 0 minus the natural log of 1/2. And so that answer is just negative natural log of 1/2, which we could leave our answer like that, but because I know rules of logs and we were actually just using rules of logs, might as well keep going with our rules of logs. That -1 can come up as a power, and this is 1/2 to the negative first power, which is 2 over 1. So this is natural log of 2. And that is the value of my integral. It is a finite value, so that means that this integral is convergent. And we were able to use, you can see my second example coming up and we'll jump right into that, but we were able to use some of our integration strategies, trying to get it all on the screen here without wiggling too much. We were able to use some of our integration strategies, in this case partial fraction decomposition. We evaluated the integral, then we took the limit as that bound of integration approached infinity, as t approached infinity, and it turned out we ended up with a convergent integral, natural log of 2. Let's take a look at the next one. Okay, in a very similar way, we're going to replace that upper bound. We can see that it's improper. This is improper type 1. And we're going to replace that upper bound with a variable. I like to use t. I have noticed that the book uses a or b, but I prefer to use t. So from 0 to t, 1 minus x e to the negative x dx. And now I'm going to integrate this. And because this guy is a product, I'm going to integrate with integration by parts. So I'm going to go ahead and use some integration by parts, and I'm going to fast forward the video through that part, and you can watch that in fast forward, and we'll come back once we get to the limit. Okay, so I evaluated the integral, I used some integration by parts, I simplified, got it down to this nice evaluation, and now we just are going to evaluate from 0 to t. This makes the work kind of nice that it boiled down to that, and so we end up with t over e to the t minus, well, when we plug in 0, we get 0 over 1, which is 0, and so we are taking the limit as t is approaching infinity. I copied that down wrong. Is approaching infinity of t over e to the t. Well, look at that. In a similar way to that last one, we end up with an infinity over infinity, which of course is indeterminate and allows me, it's in the proper form to apply L'Hopital's rule, so I can apply L'Hopital's rule to calculate that limit. And when I do, the limit as t is approaching infinity, when I apply L'Hopital's rule, that allows me to take the derivative of the top, which is 1, and the derivative of the bottom, which will stay exponential e to the t. And now I can evaluate the limit, and that becomes 1 over infinity or 0, which is finite and means that we have convergence. So this is converging. It converges to 0. This integral is converging to 0 if we zoom out and get that whole thing on the screen. Let's keep rolling and let's go through another example. So again, we have another improper integral. I see that infinite bound on the limits of integration. And so again, it's a type 1, and we're going to replace that bound with a t. We're going to integrate from 2 to t as t is approaching infinity. And this is, I'm going to rewrite that as 1 over x, natural log of x dx. Now, this one is going to be a pretty quick integration strategy because I see here I can do a u substitution. So we'll just run through this one. I don't think we need to speed up the video. It'll be pretty fast because if u is the natural log of x, then du is 1 over x dx. And I can make that direct substitution. Again, we integrate before we take the limit. So we'll carry the limit throughout. We're going to be integrating from 2 to t. This is going to become 1 over u. The 1 over x dx becomes my du. Now, I will just remember that these are in terms of x. I guess we could switch them over to be in terms of u, but I'm going to just leave them in terms of x and follow it through. So the limit as t is approaching infinity, the integral of 1 over u is the natural log of the absolute value of u. Evaluated from x equals 2 to x equals t, but that's going to be the limit as t is approaching infinity. That's where it would have saved us some time if we had switched the bounds to use. But natural log of the absolute value of it's the natural log of the absolute value of the natural log, because our u was the natural log of x. Now we are evaluating that from 2 to t. We'll plug that in, and then we'll be able to take the limit. So the limit as t is approaching infinity of the natural log of the absolute value of the natural log of t minus the natural log of the absolute value of the natural log of 2. Okay, now we can go ahead and take that limit and we think about our natural log function. Remember, if you ever have a hard time kind of visualizing it, it might help to graph it. Like there's the natural log of x. So as t, the argument of the natural log is going to infinity, the natural log itself is going to approach infinity, and so we're going to end up with the natural log of something that is approaching infinity minus the natural log of the natural log of 2. But of course, as the argument of the natural log approaches infinity in the way we just discussed, that's actually going to be infinity minus the natural log of the natural log of 2, which of course is just infinite. And since this is infinite, what that tells me is that this is a divergent integral. This diverges, it does not converge. So it's a type 1 divergent integral. We can show that through our integration and limit work here. All right, our last example on this video is going to be one of the integrals where both of the bounds are infinite. So we're integrating from negative infinity to infinity. So when we notice that this occurs, what we're going to do is we're going to say, well, let's split this up, because if I can show that two integrals, the sum of two integrals, if they are both convergent, then the integral across the whole bounds will be convergent. So we can actually pick anything we want. Turns out, actually, if we were to graph this, this is going to look something like this. I've zoomed way in because this is 1/9 right here at 0. But it's going to look something like this. And what we can do is we can think about, since it's a positive function, what we can do is we can think about the fact that we are considering if this area across the entire number line is infinite or finite, which is an interesting thought because it is across infinite bounds, but does it cover an infinite amount of area, or is it a finite amount of area? We can pick any value we want to split it, because obviously we're going from negative infinity, the far left of the graph, to the far right of the graph. It does often make sense to split at 0, but of course, if it made sense to split somewhere else, we would split somewhere else. So we're going to think about these two integrals from negative infinity to 0 and from 0 to infinity of 1 over x squared plus 9 dx. And if you want to think of it, we're splitting it right here at 0. So you could think of this as the first area we're thinking about, that first integral, and this would be the second. Now, if one of those were infinite, divergent, then the whole thing would be divergent. So we don't have to consider actually both cases, only one case if we get divergence. Now, on the other hand, if one of them's convergent, then we check that the other is also convergent, and if they are, then we can add them up, and that will be the value of our integral. So that's what we're going to do. We're going to take a look at each of those individually. Let's start with the first one. So if we take the first one, We'll just bring it down here, and we consider the integral from negative infinity to 0 of 1 over x squared plus 9 dx. We'll say that's the limit as t is approaching negative infinity of the integral from t to 0 of 1 over x squared plus 9 dx. And I notice that that is conveniently very much in the form of an inverse tangent where a is 3. And so this is the limit as t is approaching negative infinity. The integral of 1 over x squared plus 9 is going to be 1/3 inverse tangent, or arctan, of x over 3 evaluated from t to 0. So then we're going to evaluate that, take the limit after we've evaluated it across the bounds. So we're going to plug in 0, so we get 1/3. Well, inverse tangent of 0 is 0. So we get 1/3 times 0. Well, it's funny, I made an upside down heart. Times 0 minus, then we get 1/3. Now, the inverse tangent of t over 3. Now, we're going to take that limit as we approach negative infinity. Give myself a little bit more room. So we're going to take that limit as we approach negative infinity. So little recall here. This is hopefully a graph that you remember, but it might have been a bit. So let's recall. The inverse tangent graph looks like this. So the inverse tangent graph looks like this and has horizontal asymptotes at negative pi over 2 and positive pi over 2. So right here, as t is approaching negative infinity, this piece, the inverse tangent of negative infinity over 3, which is just negative infinity, is going to be approaching negative pi over 2 from our little recall here. I'll put a little star here. So as we're going out along the left side of the inverse tangent graph, as the argument is approaching negative infinity, the inverse tangent graph is approaching negative pi over 2. So this becomes, as we approach, obviously 0 becomes 0, so it becomes 0 minus 1/3 times negative pi over 2, but that's pi over 6, which is a finite value. So it definitely converges. So the first part here is converging to pi over 6. So we know it's the first part's converging. We just have to figure out if the second part is also converging. Now, what's nice about this is because it's going to be the same function that we're looking at, just the bounds are changing. We're going from 0 to infinity of 1 over x squared plus 9 dx. The only thing that's changing there is the bounds. Instead of from negative infinity to 0, we're from 0 to infinity. So we still do the same process, and our integration strategy will look very similar. We're going to take the limit as t is approaching infinity from 0 to t of 1 over x squared plus 9. But we've already thought about the fact that that is an inverse tangent integral. So this becomes the limit as t is approaching positive infinity of 1/3 inverse tangent of x over 3. And we're evaluating that from 0 to t. So we're going to plug in those bounds and then take the limit. And I'm going pretty quick through this part because we took a similar integral on the last step. So this becomes 1/3 inverse tangent of t over 3, can't go too fast that I lose things, minus 1/3, well now the inverse tangent of 0 is 0, so minus 1/3 times 0. And then we're going to be evaluating as t is approaching infinity. Well, as t approaches infinity, so this time we're going out this side on the inverse tangent graph. As we're going to infinity, the inverse tangent of something that's approaching infinity is going to approach positive pi over 2. It's going to be going along its graph and getting closer and closer to its horizontal asymptote of positive pi over 2 as we approach infinity. So this is going to become 1/3 times positive pi over 2 minus 0, which of course is pi over 6. And that converges as well. So both pieces of my improper integral are converging. I put a question mark there, but they are both converging. Therefore, the integral is going to be the sum of those two convergent integrals, which is pi over 3. And my answer here is pi over 3, and specifically, we would also say that the integral is converging. So notice here we had infinite bounds from negative infinity to positive infinity. And the way we deal with that is we split it up into two pieces. Again, we chose 0. We could have chosen anything in between negative infinity and positive infinity, but you will often see the choice of 0 because it splits nicely at 0. The number line splits in half in a way, if you want to think of it that way. And then we just integrated each piece. And if each piece converges, then the integral itself will be the sum of those two values. And there we go. All right, so we got some nice examples of type 1 improper integrals.